Alright, so in this video I'm going to be explaining this important paper with the title Graph Neural Tangent Kernel, Fusing Graph Neural Networks with Graph Kernels. So we know about tangent kernel, but this paper talks about graph version of tangent kernel. This paper in 2019. So while graph kernels are easy to train and enjoy provable theoretical guarantees, their practical performances are limited by their expressive power, as the kernel function often depends on handcrafted combinatorial features of graphs. Compared to graph kernels, graph neural networks usually achieve better practical performance as GNNs use multi-layer architectures and nonlinear activation functions to extract high-order information of graphs as features. However, due to a large number of hyperparameters and the non-convex nature of training procedure, GNNs are harder to train. So the current paper presents a new class of graph kernels called graph neural tangent kernel, and corresponds to infinitely wide multi-layer GNNs trained by gradient descent. GNTKs enjoy the full expressive power of GNNs and inherit advantages of graph kernels. So we formalize GNN framework and we refer to neighbor aggregation process as a block operation and to graph level pooling as a readout operation. So this is block level operation, the aggregation, because it aggregates feature over neighborhood summation, for example, and transforms the aggregate features with nonlinearity. When the number of fully layers is 2, the block operation can be written like this. Notice that the block operation we define above is also known as the graph spatial convolutional layer in the GNN literature. To get representation of entire graph, we use this readout function. So we have built our GNNs using this block and readout with their terminology. But what is the intuition of this GNTK, graph neural tangent kernel? Given a training data set, consider the training neural network by minimizing this squared loss over training data. So we have n training data points. And suppose we minimize the squared loss by gradient descent with infinitesimally small learning rate. So we have this learning rate. And let U be the network output. So the U follows this evolution equation, which is just a differential equation. Recent advances in optimization of neural networks have shown for sufficiently over-parameterized neural networks, the matrix H, this one, keeps almost unchanged during the training process, in which case the training dynamics is identical to that of a kernel regression. So our general strategy is like this. Let F be the output of the GNN, and then we need to calculate the expected value of this in the limit that M goes to infinity. So M is the size of your theta, and then M goes to infinity, and theta are all Gaussian random variables. So when m goes to infinity, it can be viewed as a Gaussian process. This is the main idea of this neural tangent. And now you know the idea. So a block operation in graph neural tangent kernel calculates the covariance, this covariance matrix. So we perform a neighborhood aggregation operation between two graphs G and G prime. Because we want to create a kernel, pairwise kernel value theta induced by this GNN. So these are you can substitute and check this. These intermediate outputs will be used to calculate the final output of the corresponding GNTK. So we can now calculate the final output with jumping knowledge and without jumping knowledge. So this is an illustration of our recipe that translates a GNN to a GNTK. On the right, you see graph neural tangent kernel. So that's why they defined the concept of blocks instead of aggregations, because it's different. We are working at the covariances. We are creating some kernels, neural network tangent kernel. And so this is an illustration of neural tangent theory. So consider a general network with L layers. When trained by gradient descent, the evolution is this. So one can show that when the number of parameters in the neural network is large enough and parameters of the neural network are initialized as Gaussian variable, it can be calculated analytically. So they did comparisons on different data methods like GraphSage. They compared GraphSage with GNTK or graph isomorphism with GNTK. And different data sets like NCI1, because these are good for graph classification,